Hello, welcome to video 44 in the lecture Advanced Mathematic Modeling. Now, after all these excursions into power law distributions, we can come back to our Levy flights. So we have random walks in one-dimensional space where the increments are distributed according to power law. Okay, so we can see it better. So the sign of the increment was a random number, random plus or minus, but the value, the absolute value of the distribution was taken from the random walk. And then already at this time we looked at then, so the random walk is just a cumulative sum of such increments, and then we saw that we have, when we now construct the random walk, it looks like small twiggling, but sometimes we get this rare event, and then we get this large jumps, so we get this characteristic shape of such Levy walk and then Levy flight. And already at this time we have seen the surprise. Sometimes we can have very large jumps. These are these extreme events, increments from the tail of the distribution. And this is called a flight and not a walk. We will later see there's also Levy walks. It's a flight because in the large jump the position changes tremendously. In one time step can change tremendously, and so this is more like a jumping behavior or a Levy flight, a flying behavior than a continuous walk. So that's why this is called a Levy flight. And Levy walk is something different, which we will see later. And now, with all the, we can now start to analyze what is the mean square displacement of a Levy flight in 1D. So we want the mean squared deviation of Levy flight in 1 dimension. And let's write this down. So we want the probability of the absolute value of the increments proportional to the absolute value of the increments to power law with alpha larger than 1 and smaller than 3, because if alpha gets larger than 3, we know that we already have diffusion because the standard deviation of the increments is defined. Okay, so we know that the increments, or the mean of the increments by construction, are 0. We have uncorrelated increments, so epsilon I times epsilon j, if I is not equal j, is 0, and epsilon I squared here, so the variance is infinite if alpha is smaller than 3. So this means we cannot use our usual formula for the mean square displacement, because so there were the increments, right, from our Levy walk, and now we calculate our random walk, x of n. That's the cumulative sum of our increments equal 1 to n. So I do this, I write this down again, this stuff, because we had a lot of videos in between, so that you remember. And now, so what was the expectation of the position of our walker? That's n times the average here. Expectation of the increments is 0. So on average the walker does not increase its position. And now we had the formula for the second moment. Actually I was writing the time dependence after the expectation here. Okay, so what's the second moment? And then we had our formula, that's n times the variance here of the increments plus the sum of this correlation function if I not equal j. So this term here vanishes because we don't have correlations, but this here is infinite, because we have now we have increments which come from a distribution which has no variance, no defined second moment. So this means on average the walker will always stay on 0. But what we really would like to have, we would like to know after a certain time what is the typical extent here. What's the typical position that the walker has done, maybe give it a head or something, after a time t. What is the typical position that the walker has? We cannot calculate here the variance or standard deviation because that's infinite. So, but now there is a trick that we can use, and that's also a trick which we can use in anyhow to for any power law distribution, to find what's the typical value that we expect after t samples from the distribution. And so we say, okay, mostly we have small scattering, we have increments here from the head of the distribution, and very rarely we have a tail. So we just have to look what's the largest value of our increment that we experience after time t. And then we say our expected deviation of the walker just is proportional to the largest value. And that's now the trick. So let's first write here the usual calculation of mean squared deviation does not work. So again, we see that the power law distributions are a bit weird, so we cannot calculate our normal mean squared displacement of a random walk. And now the idea is we say this typical displacement after t steps is dominated by the largest increment. So what we need now to calculate the largest increment E max, or let's call it X max because that's already this value here. So that's the maximal value of the absolute value of the increments for I equals 1 to t. So we want to know what should be the largest increment that we expect if we take t samples from our power law distributions. So we want to know, calculate, and this is quantity, that's the biggest jump after t steps. And that's the trick. We want to calculate here the biggest jump. So even in cases where we cannot calculate the second moment because it's not defined, it diverges, we can still look what's the biggest jump. But how do we find the biggest jump of a power law distributed random variable? And now we use another trick. So we transform our distribution to something which is more smooth. And then remember, when we did variable transforms of random numbers, of distributions, if we have a power law distribution, so the distribution of length L goes with L to minus alpha, it's power law distributed, then the transformed variable U, which is given as L to 1 minus alpha, is uniformly distributed. In the interval between 0 and 1. I mean, that's always the trick how we compute power law distributed numbers. We take a random variable, uniformly distributed random variable between 0 and 1, and then make the reverse transformation, and then we have our power law distributed variable L. So now we just need to know, if we want now to have the largest L, by this transformation we need to find the smallest value. So find the smallest value U min from a uniform distribution after t steps. And I will show you soon that this U min goes proportionally with 1 over the number of steps. So the minimal value, if you take t trials in the interval between 0 and 1, goes with 1 over the number of steps. I will show you this in the second. Here. And this means if the minimal value goes like 1 over t, then this L max, the maximal power law distributed variable, when we make the reverse transformation, then goes with t to 1 over alpha minus 1. If you just plug in this value here for u, and then solve for the maximal L. And this means also that in our random walk, the maximal position, or I used before the notation hat, so this x max as a function of t goes with t to 1 over alpha minus 1. And so that's here a critical exponent. And so this means here we have a scaling, and if this exponent is not 1 over 2, we have super diffusive behavior. And if you call this exponent mu equals 1 over alpha minus 1, then we can make a small plot. Here we have the exponent of our power law distribution, and here we have this mu. And then you can see this mu goes here from 1 over 2 if we have the value 3. If we have an alpha of 2, this mu equals 1. And if alpha is smaller than 2, this mu is even larger. So we have this form. Yeah. And then we see, so we can calculate the typical, it's not really the mean square displacement, but it's still the typical position that the walker has after t steps. It goes to the time, the number of steps with an exponent mu. And this mu for smaller alpha increases from 1 over 2 to 1 to something even larger. And now it's interesting, so you see for alpha larger than 3, here, we could calculate our mean square displacement. and then we have the diffusive behavior. There the typical position should go with 1/2. I mean, so here we have diffusion. So here the Walker just makes a diffusion. Now if alpha is larger than 3, we cannot use the mean square displacement, but we can use this formula, and then our critical exponent increases. So here we have super diffusion. And at this case alpha equal 2, we have a kind of ballistic movement, so the position of the Walker increases linearly in time. And if alpha is even smaller than 2, the typical position of the Walker increases faster than linearly in time. And this is possible because the Walker makes these jumps, and so it can be increased faster than linearly in time. So we have really seen, if we have a Levy flight here, with an exponent of the distribution alpha smaller than 3, we find the super diffusive behavior. So what's still missing? I have to prove that the smallest value, when we take random numbers from a uniform distribution, really goes as 1/t. I have to prove this, but maybe let's write this down here. Levy flight with alpha smaller than 3 leads to super diffusion. Okay, and now this theorem here. So let's say we have random numbers, t random numbers from a uniform distribution in the range 0 and 1. So that should be mean a uniform distribution. And so we want the probability that the minimal value of all this xt's, if we take t trials from this distribution, the minimum of all this is smaller than the value x. So that's the cumulative distribution for the minimum. And now how do we find this probability? We use our usual trick, that's 1 minus the probability that all xt are larger than x, and they are independent. All xt's should be larger than x, so that's 1 minus, now we have t times, no, we have the probability to be larger than x goes with 1 minus x. That's the probability that a random number from a uniform distribution is larger than x. And we have t of these values. This goes with the power t. So that's the cumulative distribution. And now we need the PDF. The PDF we obtain if we take the derivative of the cumulative distribution. So this p of x is then the derivative of this. So this is t times 1 minus x to power t minus 1. And now we can calculate what's the expectation, the expected minimal value. So we take the expectation of this function. So we integrate in the range between 0 and 1. We need x times p of x. This is the integral between 0 and 1. We have the t, then we have x times 1 minus x to power t minus 1 dx. Now this can be integrated, and this equals 1 over t plus 1 and this is approximately for large t equals 1 over t. So really, if we take t random numbers from a uniform distribution, so here we have a uniform distribution between 0 and 1, and we take t values, and the longer we wait, the smaller the number we get. And so we see on average the smallest number goes with 1 over t. Okay, and that's also the trick to find the typical increment in a power law distribution, if or in the distribution where the second moment is not defined anymore. Okay, so we have seen Levy flights in 1D are typical examples of super-diffusive behavior. So you can have super-diffusive behavior when jumps are taken from a power law distribution. And now in the next videos we will continue to look at the geometry of random walks. For the moment, thank you.